under the eternal stars that had witnessed the entire sweep of Mesopotamian history, the people of Babylon rested peacefully in their ancient city, confident that their contributions to human civilization would outlast any political changes that the future might bring. They could not have imagined how prophetic their confidence would prove to be. That innovations born from practical necessity in the first cities would become the hidden architecture of modern life, governing everything from the time we wake each morning to the navigation systems that guide ships across distant oceans. The priest-astronomers climbed the ziggurat steps in pre-dawn darkness, their sandaled feet following a path worn smooth by thousands of years of nightly observations. At the summit of ancient Babylon's Great Tower, they prepared instruments that had been refined across generations of patient study. Bronze astrolabes for measuring star positions, water clocks for tracking time's passage, tablets of baked clay ready to receive the precise notations that would extend humanity's oldest continuous scientific record. This nightly ritual, performed without interruption for over 2,000 years, represented something unprecedented in human history: the systematic accumulation of empirical data across time spans that exceeded individual lifetimes, creating scientific knowledge that could reveal patterns invisible to casual observation. What began as religious obligation had evolved into humanity's first rigorous investigation of natural phenomena. The base 60 mathematical system they used for these calculations continues to govern our daily lives 5,000 years later. Every time we check a clock divided into 60-minute hours, every time we navigate using the 360-degree circle they invented, every time we measure angles in the geometry that shapes our architecture and engineering, we unconsciously employ innovations that emerged from Mesopotamian temples, where priests sought to understand divine patterns revealed through celestial motion. Their mathematical genius was born from practical necessity. Managing irrigation systems that served hundreds of thousands of people required precise calculations of water flow, field areas, and grain distribution. Coordinating urban life among populations larger than anything the world had previously known demanded numerical methods that could handle complex transactions and administrative requirements. But Mesopotamian mathematicians achieved far more than practical adequacy. They developed the first positional notation system, where a digit's value depended on its position within a number, the fundamental concept that makes all advanced mathematics possible. They created algebraic methods for solving complex equations, geometric techniques for calculating areas and volumes, and trigonometric principles that enabled accurate measurement of distances and angles. Most remarkably, they discovered mathematical relationships that would not be formally proven until millennia later. Babylonian tablets contain approximations of square roots accurate to 6 decimal places, calculations of compound interest that demonstrate sophisticated understanding of exponential growth, and geometric theorems that anticipate discoveries attributed to later Greek mathematicians. The astronomical observations that provided data for these mathematical investigations were equally revolutionary. Mesopotamian astronomers created the first comprehensive star catalogues, mapping constellations and tracking stellar positions with precision that enabled prediction of celestial events years in advance. They identified the planets as wandering stars, whose motions followed different patterns from the fixed stellar background, developing mathematical models that could predict planetary positions with remarkable accuracy. Their discovery of the Saros cycle, the 18-year pattern that governs solar and lunar eclipses, represented one of humanity's first successful predictions of natural phenomena through mathematical analysis rather than supernatural interpretation. This achievement demonstrated that apparent chaos could conceal discoverable order, that human intelligence could penetrate mysteries that had previously been accessible only through divine revelation. The calendar system they developed to organize agricultural and religious activities became the foundation for timekeeping throughout the civilized world. Their division of the year into 12 months, their recognition that lunar and solar cycles required complex coordination, their creation of leap year adjustments to maintain seasonal accuracy, These innovations were adopted by every subsequent civilization that sought to organize human activities according to celestial rhythms. But perhaps their most profound contribution was methodological. The demonstration that systematic observation and mathematical analysis could reveal universal principles that governed natural phenomena. This approach to understanding the world would eventually evolve into the scientific method that underlies all modern knowledge, but its origins lay in Mesopotamian temples, where priests recorded celestial observations with religious devotion that happened to produce rigorous scientific data. The medical knowledge that developed alongside these mathematical and astronomical investigations reflected similar commitments to empirical observation and systematic analysis. Mesopotamian physicians created the world's first diagnostic manuals, describing symptoms and treatments for hundreds of different ailments based on clinical experience rather than purely theoretical speculation. Their pharmacological texts catalog thousands of plant, animal, and mineral substances used as medicines, often with surprisingly accurate understanding of effective dosages and administration methods. Modern analysis of these ancient prescriptions has revealed that many contained compounds now recognized as therapeutically active, suggesting that Mesopotamian medicine achieved practical effectiveness through systematic experimentation rather than mere trial and error. The surgical techniques described in cuneiform medical texts demonstrate sophisticated understanding of human anatomy and surgical procedures. Descriptions of cataract removal, kidney stone extraction, and bone setting reveal medical knowledge that would not be surpassed for centuries, while the emphasis on wound care and infection prevention shows awareness of principles that modern medicine has validated through scientific research. The engineering achievements that transformed Mesopotamian landscapes into productive agricultural systems required mathematical and scientific knowledge that rivaled any practical applications until the modern era. The irrigation networks that converted wetlands into fertile fields involved hydraulic calculations of remarkable sophistication, while the urban planning that created the world's first cities required understanding of drainage, sanitation, and construction techniques that solved problems no previous civilization had faced. The invention of the wheel, perhaps the most revolutionary technological innovation in human history, emerged from Mesopotamian workshops where craftsmen sought more efficient methods for shaping pottery and transporting goods. This simple concept transformed everything from daily transportation to complex mechanical devices, becoming one of the fundamental principles underlying all later technological development. The architectural innovations that created ziggurats, palaces, and urban complexes capable of housing hundreds of thousands of people required engineering knowledge that solved structural problems through mathematical analysis and empirical testing. The arch, the dome, and other architectural elements that would become standard features of construction throughout the world were first developed by Mesopotamian builders, who needed to create large interior spaces using available materials and techniques. The metallurgical knowledge that enabled the production of bronze tools and weapons, and later iron implements that were superior to anything previously available, emerged from systematic experimentation with ore processing, alloy composition, and heat treatment methods that represented applied chemistry centuries before chemistry existed as a formal discipline. But perhaps most remarkably, all these practical innovations were preserved and transmitted through writing systems that enabled accumulation of technical knowledge across generations. The cuneiform tablets that recorded mathematical calculations, astronomical observations, medical treatments, and engineering techniques created humanity's first technical libraries, where craftsmen and scholars could access information developed by predecessors and contribute their own discoveries to an ever-growing repository of human knowledge. This systematic preservation and transmission of practical knowledge represented a fundamental transformation in how human societies dealt with technical challenges. Instead of each generation having to rediscover solutions to problems their ancestors had already solved, accumulated knowledge could build upon previous achievements to reach increasingly sophisticated levels of understanding and capability. The influence of these Mesopotamian innovations spread throughout the ancient world, through trade networks, military campaigns, and scholarly exchanges that carried both specific techniques and general approaches to problem-solving far beyond their original geographical boundaries. Greek mathematics built upon Babylonian numerical methods, Roman engineering adapted Mesopotamian architectural techniques, and Islamic scholars preserved and extended astronomical observations that had begun in ancient Iraq. Modern science and technology remain fundamentally dependent on innovations that emerged from Mesopotamian civilization. Mathematical principles that enable computer programming, the astronomical knowledge that guides space exploration, the medical understanding that makes modern surgery possible, the engineering methods that create contemporary architecture, all trace their origins to discoveries made in ancient cities between the Tigris and Euphrates rivers. As evening settled over the modern world, as artificial lights replaced oil lamps and electronic devices substituted for clay tablets, the intellectual foundations established by Mesopotamian civilization continue to support human achievement in ways that most people never recognize or acknowledge. In research laboratories, where scientists use base 60 mathematics to calculate molecular structures, in observatories where astronomers employ geometric principles first developed in Babylonian temples, in hospitals where surgical techniques preserve medical knowledge that began with cuneiform texts, the patient work of ancient scholars continued to serve human needs 5,000 years after their physical civilization had vanished. The science of the stars that had emerged from religious devotion had evolved into systematic investigation of natural phenomena that continues to expand human understanding of the universe. The mathematical methods developed to manage urban life had become the analytical tools that enable modern technology. The engineering knowledge that created the first cities had grown into the technical capabilities that shape contemporary civilization. Under the same eternal stars that had inspired the first systematic observations of celestial phenomena, modern humanity rested peacefully in cities whose fundamental organizing principles, timekeeping systems, and technological foundations remained dependent on innovations that had emerged from humanity's first urban experiment in the wetlands of ancient Iraq. Tomorrow would bring new scientific discoveries, new technological innovations, and new applications of mathematical principles that had been established when human civilization was young. But the intellectual framework that made all these achievements possible had been established by anonymous scholars working by lamplight in ancient temples, patiently recording observations and developing analytical methods that would prove more durable than the political empires that had commissioned their work. Our journey through the corridors of time continues as we step away from the grand sweep of empires and innovations to discover how ordinary people lived their daily lives in the shadow of the great ziggurats. Experience the rhythms of family life, work, and celebration that gave meaning to existence in humanity's first cities. The voices of common folk await